Hello everyone, welcome back to my YouTube channel. In this video I am going to show you how we can do a simulation for current distribution in a bus bar. In later video we will use this basis for the simulation of battery cells where we will be applying electric current instead of constant heat supply. By the way, in the description I have included Amazon links for some good CFD books and useful tools. Using these links also support the channel. You can also support the channel via PayPal. So let's see a very basic simulation for the current distribution in a bus bar. For that, let's create a sketch. I'm going into the sketch mode. I'm creating very simple bus bar. I am creating some lines, 30 millimeter, 10 millimeter, 50 millimeter, and then I'm just going down. It is 10 millimeter and then 30 millimeter. Let me create round edges. In a minute you will see how it will look like. 1 millimeter is fine, then 1 millimeter is over here. I'm just making round corner. 1 millimeter radius I want to have, then 1 millimeter radius over here. It looks fine. Now I will extrude this line to create a surface, and I want to extend in both direction, and I will have 5 millimeter. It looks fine. Then I will select all these surface and extend from center in both direction, and I will extend by 1 millimeter. Okay, it looks fine. Now I want to create two holes. One is over here, one is over here for electrical connection. For that I will go to the sketch mode and I will select this as a surface, and now I will create a hole. I'm just creating without any dimension. 2 millimeter over here and 2 millimeter over here. We will go back to the 3D mode and I will extrude these circles, this one into the other direction. It will remove this surface, and same over here. Now our bus bar has been created. Let's move to the meshing. Now we are in meshing module. Before moving forward, just let me see its surface area. It is important, 6.2 millimeter square. I will let you know later why do I need this one. And let me give some naming. This one, let me call this one as current, and the other one, let me call this one as potential. And let's say we will have some convection only on the upper surface, all this top surface. Press N and I can call this convection. Now let me create mesh. First I'm just creating the default parameters. It is 2 coarse. I can make it finer. For that I think 0.5 millimeter should be fine, and I can say generate mesh. It looks better, but I would prefer a little more finer generate. Now it looks good. Let's move to the Fluent for the simulation part. I am in Fluent module. First I always change unit. I always use Celsius. You can use Kelvin or Fahrenheit, whatever you use. That's it. Then we have to go in model. I will be running a steady state simulation. I will go into the model. Energy equation. We need energy equation because we will be seeing the temperature distribution on this surface as well. Then we also want to see this potential equation. For viscous we don't need viscous because we will not be doing any fluid, but let's say it laminar. And then we have this potential equation. We also have to activate this potential equation, and I want to include Joule heating. I am not doing any electrochemistry, so I just need Joule heating. Okay, we have activated our model. Then we will go to the material. I will be simulating aluminium, considering this bus bar is of aluminium. Then cell zone, by default it is saying fluid, but we have this solid, so I will say this one is solid. Now let's define our boundary condition. We have all the walls. I have already given the name current. Okay, I told you the area was 6.2 square millimeter. If we go into the potential, here we can define current density. It means we have to calculate our current density. Let's say we are saying 100 ampere current is passing. Let me open the calculator. 100 ampere, and I will divide it by area. Area was 6.2 millimeters, so it is 0.0062. That is in meter. So it will be 16,130. 16,130. It is approximately 100 ampere. Apply, close, then potential, and we will go again in potential. We have defined our current density. Then I want to specify potential, which is in specified value, and now you can see potential is 0. So I am defining current on one side and 0 potential on the other side. I will say apply and close. Then I have another wall where I want to define my convection, and I am saying 10 watt per meter square per Kelvin, and free stream temperature is 25. Apply and close. I have defined all the boundary condition. That's it. Then we can check our residual. Energy equation 10 raised per minus 6 and potential 10 raised per minus 9. These are fine. I can initialize. I'm doing hybrid initialization, and then I can run my simulation. Let's say I'm running for 500 iteration and see how long it will take to converge. Our simulation has converged. Let's see our temperature distribution and our current distribution. Contour, temperature, select all, save display. Here is our temperature distribution. Temperature did not change at all, so it means we have very less heat generation, and it is a metallic, and we have convection on top. Therefore, we hardly see any temperature rise. To see the temperature rise, we can maybe use higher current density. I will check later. Before that, let me show you the current distribution. I will go to the potential, then electric potential, no, electric current, and I will say save display on those surfaces. Let me create a surface at the center, plane, XY plane. That's fine. Create, close, and I can see the current distribution. Here is our current distribution into the bus bar. Here are some higher current density, and also on these edges some higher current density, and on near wall we have much lower current density. So maximum current is in the range of 2000 ampere, and near top and bottom wall it is nearly 0. So we do not get the uniform current distribution inside the bus bar. And we can also see the Joule heating. Here is our Joule heating, and you can see heat generation is very less. It is in watt per meter cube, 40 watt per meter cube. So for 1 meter cube we are having 40 watt, which is extremely low. So that's why we hardly see any temperature rise. Let's give a crazy number for current and then see if we get the temperature distribution. For that I will just change the current value. I am giving over here, it's 16,000. I don't know. Let me give 1, 2, 3, 4, 5, 6. I have just given some number. I just want to see the temperature distribution. Apply, OK, calculate. I will run simulation for few iteration, then I will stop the iteration just to show you. We will see some temperature rise. We have already some simulation data. I can stop. It is not converged but should be okay. I am going over here and I want to see the temperature distribution. Okay, let's see on this plane. Now you can see our ambient temperature is 25 degrees Celsius, maximum temperature is 27, and temperature is uniform approximately because minimum is 27.6, maximum 27.7, because it's aluminium rod and we have convection on all the surface. It means it has uniform cooling, that's why we see the uniform temperature. We can display our entire surface. That's how our bus bar will look like. Temperature will rise only by 2.6 degree for this crazy amount of current. Anyhow, that's how you can simulate your current distribution and your heat generation into the Fluent. In next video, I will make a comparison of two battery cell. In one of the cell, I will directly supply heat generation because heat generation will be uniform in entire cell. On the other side, I will give a current as an input and heat will be generated through Joule heating. Then we will see if these two have impact on the battery cell temperature, because we have seen over here, let me bring back that one, potential, plane and display, because you have seen we do not have uniform current density. It means heat generation will also not uniform. We might see some effect, but we will see in our next video. That's it for today. Thanks for watching and see you in the next video.